Hello, this is the Johns Hopkins Undergraduate Brain Computer Interface Society. In this presentation, we would like to show what we have achieved with our project, which is titled Regression-Based Intuitive Continuous Neural Process Control. Our product aims to achieve regression-based continuous neural processes control. For some background, a neural prosthesis is a motorized prosthesis that can be controlled through a brain-computer interface, or abbreviated as BCI. The most common approach for neural prosthesis control is to use a classification algorithm to decode BCI signals, where the BCIs used for this purpose are mostly electromyogram based, or EMG. However, this is counterintuitive as we do not control our movement as categories, but rather different degrees of contraction of each muscle. Therefore, to achieve truly intuitive prosthesis control, our approach is to train regression algorithms to decode continuous muscle contractions from EMG signals.
In our case, the BCI hardware we used is a myo-EMG armband, which can be worn on the forearm and collects 8 channels of EMG data. To acquire data from the BCI hardware, we use Mini-VIE, which is an open-source package library developed by the Johns Hopkins University Applied Physics Laboratory. We decided to decode continuous contractions of each finger as a starting point. This is a feasible approach since the muscles primarily responsible for finger contractions lie in the forearm, and for amputees that have lost their hand, this approach has the potential to provide them with a neuroprosthetic hand that can control just like how they would control their natural hand. Conventionally, finger contractions would be measured mechanically using glove-based hardware such as CyberGlove, yet such hardware is often very expensive. In order to reduce training cost, we decided to adopt AI hand pose estimation with MediaPipe, which is a variant of the open-source MediaPipe hand recognition package. This slide shows flowcharts of how we train and plan to implement our system for intuitive continuous neural prosthesis control. In training, the user performs hand gestures, aka contracting their fingers, which are then recorded both with the BCI devices, which is a myo-EMG armband, and with MediaPipe hand gesture recognition. Using the EMG data as an independent variable and the MediaPipe recorded finger angles as a dependent variable, we can train a regression algorithm to decode EMG signals into finger angles. Once the regression algorithm is trained, it can be implemented for real-time neural prosthesis control. In this situation, EMG data is collected and decoded in real time while the user attempts to perform hand gestures. The decoded finger angles can then be directly performed by the neuroprosthetic hand.
Our first attempt to develop a decoding algorithm involves the random forest regressor used in conjunction with principal component analysis, or PCA. The main advantage of this approach is that this is a classic algorithm for nonlinear regression, which is easy to tweak. Nevertheless, it also has certain disadvantages. For example, the random forest regressor by design does not recognize the time context of the input data, or in other words, the historical data points, which happens to be an important feature of neural signals, including EMG signals. Furthermore, PCA cannot be performed by any particular data point, but rather a data set, which means that it cannot be applied to real-time data points. To mitigate these drawbacks, we considered 2 corresponding solutions. With regards to the time context, we decided to not shuffle the training data so that the training and testing sets each retain the time context. With regards to the conflict between PCA and the real-time applications, we may potentially collect a few of the most recent historical data points that we call the buffer and apply PCA to the buffer for decoding. This allows us to achieve pseudo-real-time decoding. As long as the size of the buffer is reasonable, the delay in the decoding shall not cause significant inconvenience.
Let's move on to how the details of the algorithm was trained. First, EMG and finger angle data were collected with the mount armband and laptop webcam, respectively. During the data collection stage, an important detail is to note how important the user collected the data. The user needs to contract their fingers in such a way that they're mostly using the muscles in their forearm. This ensures that the highest quality EMG data is collected. Features are then extracted from the EMG signals by using a root mean square over a sliding time window. A dimensionality reduction technique, known as PCA, was used to reduce the dimensionality of the feature matrix. This reduces the dimensionality from 8 to 5, since there are a total of 5 fingers per hand. Lastly, the components extracted from PCA are used to train the random forest regressor. In order to further improve the performance of the random forest regressor, a grid search was used to find the most optimal hyperparameter configuration. Next is a video illustrating of how a participant collected the data. Note that the webcam collects the finger eagle data using media pipe. And the sensor on his forearm collects the EMG signals.
Here are our preliminary training results. On the plus, the horizontal axes are the time points which are roughly 20 milliseconds apart, and the vertical axes are the finger angles in degrees, with 0 degrees being the most contracted and 180 degrees being the most extended. The blue curves are the ground truth measurements, and the orange curves are the raw predictions from the algorithm. As you can see, the raw predictions are able to roughly track the ground truth, which means that the algorithm is able to identify the contraction in each finger. However, there is significant high-frequency noise. In order to remove the noise, we decided to employ extra processing to the output data. More specifically, we tried frequency filtering and capturing the envelope of the waveform. In this plot, the blue curves are still the ground truth, whereas the orange curves are the filtered predicted data curve, and the yellow curve is the lower envelope of the predicted data curve. The filter we used to remove high-frequency noise is a second-order Butterworth low-pass filter. As for the envelope, we used the MATLAB envelope function to capture the lower envelope determined using spline interpolation over local minima of the signal. Qualitatively, the low-pass filter removes the noise but does not follow the ground truth well when the finger is contracting. In comparison, the lower envelope tracks contractions better, but it's not resistant to the noise when the finger is relaxed.
Our work is far from complete. In terms of future directions, we aim to improve our algorithm and complete the control system for the neuroprosthesis. To improve the algorithm, we may try to implement more advanced machine learning algorithms capable of nonlinear regression, such as recursive neural networks like long short-term memory network or other types of neural networks. Alternatively, we may employ better output processing and tuning, possibly with a PID controller. Furthermore, we could collect more high-quality training data so that the algorithms can be better trained. To do so may require us establishing a well-guided training routine. After we've completed training for the neuroprosthesis, we can then move on to complete the control system for the neuroprosthesis, which will be a neuroprosthetic hand. We would like to complete the pipeline by adding the part that sends data in real time to the prosthesis and possibly with tactile feedback. Another possible direction we could follow would be to diversify the input data. So far, we've been using only EMG as input, yet thanks to generous support of Neurotech X and OpenBCI, we now have a 16-channel EEG headset to work with. Since both EEG and EMG are known to enable non-invasive neuroprosthesis control, it would be valuable for us to explore and compare the performance of EMG input alone, EEG input alone, and EMG and EEG inputs for neuroprosthesis control. Using EEG along with EMG may enrich the input dimensions, which can potentially include more features for decoding, thus enabling better decoding performance or higher dimensional output.
So for a brief summary, the aim of the project is to achieve truly intuitive, regression-based continuous neural processes control. Our approach so far is to use EMG-based input and train a regression algorithm to output angles of finger contractions. The regression algorithm we adopted is the random forest regressor in conjunction with the principal component analysis, and low-cost training is achieved by using media pipe hand gesture recognition. The preliminary training results we have obtained show that it is indeed possible to use a regression algorithm to capture finger contractions, yet there is a significant high-frequency noise in the raw prediction. The noise can be handled by further processing with methods such as low-pass filtering or capturing the envelope of the predicted output. Our future plans so far include developing a better decoding algorithm, then completing real-time decoding for actual neural processes control, and exploring multimodal input using both EMG and EEG for neural processes control. These are our main references, and thank you so much for listening to our presentation. We look forward to continue our project into next year. So see you next year.